Anyone started the assignment yet? Is there any template for individual assignment for MLPC, or we can just take and modify from the template? Yes, you can just take and modify from the template. MLPC question in Cvnlp class. MLPC individual assignment consists no coding, correct, no coding, just proposal of ideas and literature reviews. Yes, correct. Not really, because I think the terms you use are quite hard to understand. Maybe with more examples could help. Okay, got it. Got you. Which terms are quite hard to understand? Can you specify any difficult words? Or maybe you can tell me during tutorial or practical class, okay? Did you remember anything from the previous lecture? You don't? Huh? Are you serious? Dinner? Yes, feel free to have dinner inside this class. Just make sure that you clean up the mess, okay? Thank you. Love your teaching style and answering questions. Yeah, you will be expecting more questions from me, yeah? Hope you love the final exam questions too. 3 has fallen. Oh yeah, I heard about the news. Hope no one is trapped. MLPC again. MLPC, are we learning basic algorithms? Yes, we are learning basic algorithms. Are there any advanced ML algorithms we're going to learn? What advanced ML algorithms? Deep learning, neural network, and deep learning. No one remember anything from the previous lecture. So, this debate and discussion returns. Nobody remember anything from the previous lecture. The only thing you remember from the previous session is assignment. Great. Some history. Yes, some history. Supervised learning. Supervised learning, are you sure? Supervised learning was mentioned in MLPC class, not Cvnlp, yeah? No, this term is not mentioned at all. No. I think because history is boring. Got you. Okay, history is boring. It was basically about the review of history with first focus on computer vision, then we follow the algorithm as well. Yes, that's right. Have you seen the AI brandings, like AI rice cookers, which are just using some smart screen tag from 2011? Yes, I suppose. Let it go. Don't let it go. Hang in there. Okay. So, does anyone still need the attendance code? Okay, so let's start our lecture today. Nobody remembers anything. No worries. We'll do a recap. So this week we are talking about digital images. So we are going to start something technical about computer vision finally, and we are going back to the very fundamental this week. So just a recap on what happened last week. What have we discussed last week? We sort of talked about the evolution of computation power, and then evolution of availability of data, which is available on the internet. And we also talk a little bit about the evolution of algorithms, how these algorithms, which is used in computer vision, specifically on the task of image classification, has evolved over time. So then we talk about convolutional neural network, which is everywhere and which is commonly used in image classification task in a lot of areas of research. So now, the keyword from last lecture was image classification. The evolution so far has enabled a lot of image classification to happen. So image classification is a very important computer vision task in today's world. So it is a basics of all the object recognitions, regardless in which field, right? So what is image classification? So classification is a task that we want this computer to do whenever we subject an image to the computer or the system, and the system itself will be able to give us a set of expected output. Say, for example, we are expecting 5 of these outputs, say cat, bird, deer, dog, truck, and once we give the computer or the system an image of a cat, we are expecting this computer vision system to give us an output to give this image a tag, which is of its correct category, which is a cat. So this classification task is so easy to human because this is just so common. It can happen within milliseconds of time. But how do we then train computer to be able to do this task as fast as humans do, right? Why is it difficult for computer to do the task as fast as human speed? Is because what computers see is different from what human sees. So for example, we as human, we see a picture of cat and immediately our brain can perceive it as a cat. And we know immediately that the category of the image is a cat. However, when the computer sees this image, what is it actually seeing? It is seeing a big grid of numbers. And what are these numbers about? And in order for the computer to see these numbers, this image that we subject to the computer or the system has to be a digital image. So now, what is a digital image and what is a real image? This is the first topic of today's lecture. So today we are going to talk about what is digital image, how these numbers that the computer see comes about. Then we'll have a quick comparison between what's real image and what's digital image. Then we'll go through again what is digital image processing. So digital image processing are ultimately tasks that we want computer to be able to conduct. So we'll talk about some areas of digital image processing, history of digital image processing, applications of digital image processing, and some components of digital image processing. So now, first thing first, what is digital image? So on the screen, you are now seeing two images. One of them is the real image, while another one is a digital image. So at a glance, we can see that the real image is clear without any boxes, while digital image are made up of boxes, of grids, of colors. So a real image is the image that is formed by actual intersection of the light rays on a certain surface, whereas a digital image is the image that is represented by a series of numbers or pixels. So pixels is the most basic unit of any single digital image. Okay? So next, we are going to talk about what this function is about. So this function is different between the real image and the digital image. So now, what is real image? We mentioned that real image is actually formed by the intersection of light rays on a certain surface. So real image, they are continuous representation of light intensity in two dimensions, in X and Y. So how is it usually represented is with a function of G and with the spatial coordinates of X and Y. The value of G here in any real image is proportional to the brightness or the gray level of the image at a particular point. So they are continuous and they are not discrete. So every single point here are continuous. So then, real image, they are representing the visual contents that is similar to our human eye. Say for example, we look into mirror and we see ourselves, and what we are seeing is actually a real image because that's continuous. So they are captured directly from the physical world using camera or imaging devices. So they don't have a pixel-based structure. So here, when we mention cameras and imaging devices, they mean the film cameras, yeah? They are not bound by discrete values. So on the other hand, in order for the computer to process this image, this real image has to be converted into a form that is digital image. So digital image is a type of image which is formed through two processes, which is called sampling and quantization. So the digital image is usually represented by the function of I in M and N. So they are the samples of the function of G, which we see previously in a particular coordinates. So I is the intensity at M and N, and M and N must be integers. So in order to get or to convert X and Y into M and N, it takes two processes, which is sampling and quantization. Okay, so digital image has this characteristic. They are usually pixelated. Pixels are the most basic unit of any digital image. How are they being pixelated? Is through two processes, sampling and quantization. So they are the representation of real images in a digital format, and they are obtained by converting the analog signals from real images into discrete digital values in grids. So why do we need to have this digital format of image? It's because this will allow us for easy storage, for transmission, to send picture from one location to another, and also to allow it to be processed by computers and also algorithms. Got it? So that is our first topic today, the differences between real image and a digital image. How are we going to convert this real image into digital format, which can be processed by computer or algorithm? Questions? Very straightforward. No questions. So then, which one of the following is a real image? Can you pin on the correct answer? So, it is a photograph printed on paper. So, we can easily edit and manipulate only real image, only digital image, neither of both, or both. Yes, we can only easily edit and manipulate digital image. The quality of a real image can deteriorate over time, while a digital image is always perfect, can be easily copied without losing quality, can be corrupted or damaged, both B and C. Both B and C, because they can be easily copied without losing quality. They are not always perfect because they are pixelated. It depends on how good our sampling is to define how perfect the images are. And because they are stored in digital format, therefore they can be corrupted or damaged. Okay? What is the smallest building block of a digital image? Correct. That's a pixel. So now what is pixel? So we have already mentioned that digital image consists of a regular collection, usually grid of samples or pixels. So what is pixel? Pixels is a short for picture elements. So they are point samples. So these point samples, they are taken to measurement taken at a specific position, and therefore it forms a digital image. So some common understandings of what pixels are is a pixel is a point sample, and an image is a regular grid of point samples. So a lot of pixels make up one digital image. So then, what are these pixels' value? And what do they actually represent, usually represent? So pixels are this single unit, the boxes, which consist of colors. So the pixel values, earlier when we see what computer sees in the picture of the cat, we see some numbers. So those are pixel values. So they typically represent the level of gray levels, or they can also represent sometimes the colors, or sometimes they can also represent opacity. So there are a few formats which are commonly used. One of them is one sample per point. So those images are usually black and white or grayscale. So this value will scale from 0 to 255. So there are 256 of them, and 0 is considered one of the value. Some images have 3 samples per point, especially those colored image. So the 3 samples per point represent red, green, and blue. This is just one of them, and there are also other representations of colored image, but RGB is the most commonly used ones. And some images, in some of the digital images, each of the points are represented by 4 samples. So what is the 4th sample here? Sometimes the 4th sample here refers to alpha, which is a representation of how opaque the image is. Okay, so that is about image. So just to recap on what have we just covered earlier, how many types of digital image are there? So the three main types of digital images are the binary image, which is black and white, the grayscale image, which is pictures, which is formed by shades of gray, and finally we have the colored image or the RGB image. So in binary image, the black and white images, the representation of pixels, they are just 0 and 1. So 0 representing black and 1 representing white. Grayscale images, so each pixel is a shade of gray. So there are 256 values of them, where 0 is considered one of the value. Therefore, it ranges from 0 to 255. So again, 0 represent black and 255 represent white. Same as the colored image. So for colored image, each of these pixels represent 3 values. So 1 value red, 1 value green, and 1 value represent blue. When 3 of these colors combined, and they become the colors which is perceived by human eyes. Okay, questions? This is again something very fundamental, something that we have to begin learning before we dive into a computer vision task. Okay, so do we use hexadecimal to represent colors? No, we use integers. We have already mentioned that M and N, they have to be integers. Can I get the attendance code? Missed it just now. Yes, later maybe. What is quantization? We'll come to that in the next session. How does binary image know what is 1 and what is 0? Through sampling and quantization. What does 1 sample, 2 sample, 4 sample per points mean? So it means this is 1 sample per points. That means each of the pixel is represented by 1 value only. So for black and white and grayscale image, they are usually represented by 0 or 1, 0 to 255. However, in the colored image, each of the pixel consists of 1 red value, 1 green value, and 1 blue value. Therefore, each pixels have 3 samples per point. So if, let's say, we need to include an opacity to the image, we will have the 4th value, which represents the opacity for each pixel. Okay? Question. A grayscale image uses shades of gray. Color images typically use three or more channels. When we convert a color image into a grayscale image, what happens? Yes, we are reducing a number of color used to shades of gray. That means we are changing it from a 3 sample per point into 1 sample per point, because grayscale image is a 1 sample per point. Okay? So, cool. Next, we are going to talk about how do we turn these analog images into a digital image. So the process is called digitization of images, which we will talk about 2 processes, sampling and quantization. So in order to convert this analog image into a digital form, we need to apply sampling and also quantization. So step 1, we have a real image, which is a continuous image. So this is any form of image in its original. So meaning it has very smooth variation of colors and intensity across the spatial dimension, across the space. It is continuous. So then, what we are going to do next is, it has a variation of brightness and gray levels, the function of G in X and Y. So these variations can range from very high value to very low value. So take an example of this point here. We can see that towards the middle, the images are very black. Therefore, the values are very small because 0 refers to black. Black equals to 0, right? So this is the representation of a real image. So how does this analog signal can be changed into, can be turned into the digital format? So in order to convert this point into a digital format, we need to apply sampling and quantization. So what is sampling and quantization? Sampling is deciding how many points do we want to take. Instead of one continuous line here, sampling is a process of picking out the points that we want. So this gives us the pixels. And quantization is the process of quantifying how dark should each of the sample point be. So first, we apply sampling to decide how many points do we want, and then we transform the intensity into a format of intensity in terms of a discrete values. Therefore, no decimal points. Okay? Got it? So that's sampling and quantization. So in more detail, sampling is, again, the process of converting the continuous signal into discrete signal. So we are selecting point to point from a continuous signal to produce this digital image. So here, sampling is a process of dividing this continuous image into grid of pixels. Again, yeah? So it represents the sample of the continuous image at that point. So what it actually affects or decides is the resolution and the size of the displayed image. So say, for example, if let's say we have the sampling rate is very high in this case, we have a picture with a higher resolution. It is a sharper image. But when our sampling rate is low, we can see that the resolution of the image would be low because we are sampling many points which are very far apart. We are sampling very little points from a real image. Got it? So that is the process of sampling. On the other hand, quantization, it is the process of converting this continuous range of intensity into discrete range of values. So it assigns this discrete value to each of the sampled boxes, which we have done during the sampling process. So this value usually represents the intensity of pixels in the original image. So what does it mean? So when our quantization rate, this quantization rate, it will affect the intensity of each sample points. So say a 1/8-bit image, they will have a higher quantization rate. Therefore, the color is richer if the quantization rate is higher. So whenever the quantization rate is low, we can see that the image is very lack in contrast. Okay? So again, these are two very important concepts in digital image, in the formation of digital image. So let's recap. Sampling is a process of converting this continuous signal into discrete signal. At the same time, once this process happens, quantization is also happening, where it changes the continuous range of values into discrete range of values. So next, this sampling, it divides the continuous image into pixels, into boxes, into pixels. While this quantization, they will assign a value to each of the grid of pixels in digital image that forms what digital image is. So each pixel here in the sample image represent the continuous image at that particular point, and this value, the intensity, is formed or is given to the digital image through quantization process. Okay? Clear? So sampling and quantization. So in short, what we just talked about is two processes that turns analog or real image into a digital image. So sampling is a process of turning continuous image into discrete data points into pixels. Quantizations assign specific colors to these data points. So altogether, we can form a digital image which has discrete and pixel-based structure. So this will allow us to manipulate it for easy storage, to transmit these images, and to process these images by computers and algorithms. Okay? Questions? How quantization assign color to pixels. So it quantifies the intensity of the light in the original pixel. Hi. Got it? It quantifies the intensity of light of a certain channel or in the original image. Right? How does the computer or algorithm know what specific value to assign the color values? Through quantization. Okay? Sampling in the context of digital image refers to yes, converting continuous analog signal into discrete values. Apa khabar? Hi, apa khabar? Sampling rate determines. Sampling rate determines. Yes, the resolution, which is also the level of detail captured in the image. Higher sampling rate results in sampling. Yes, a more accurate representation of signal. So now we are going to talk about next. Now we see the changes from real image to digital image, which means that we have a form of image that can be processed by computer. So the process and all of these processes are generally classified as a big topic called digital image processing. So let's take a look at what are the main areas of digital image processing. So some of the common areas of digital image processing are image processing, image analysis, and also image understanding, which is the modern application of computer vision. So the main areas of digital image processing can be divided into 3 levels. So at the very low level or the very earliest stage of computer vision, we are working around with the very low level image processing. Some of the operations that is involved in this kind of low level image processing are things like how do we reduce noise, how do we increase noise, how do we change the sharpness of the image itself, of the digital image. So some of the common applications of that include restoration, image restoration, as well as image compression. So those functions which we commonly see or use every day, they are one of the very low level, which is very low level digital image processing steps, which is already well established. Okay, so the inputs and outputs are images. So at the mid-level digital image processing steps, what we are trying to teach or allow computer to do are analysis and understanding. Ultimately, how do we make computer understand? Read those numbers and understand those numbers. So some of the tasks which is involved in this mid-level understanding include segmentation, which we discussed in the historical timeline. So segmentation, partition an image into regions or objects. So how do we classify these images of the individual objects? These are considered as a part of the mid-level digital image processing. So why is it moving on from low level to mid-level? Is ultimately because we are giving this computer an image and we want this computer to give us another output, which is tell me what it is. So tell me what do you see, things like that. And the output is not just another image, but the understanding about that image. And therefore, it is a mid-level digital image processing. So at a higher level of digital image processing, what we are trying to train this computer to do is to make sense of this recognized object. So once you recognize this object, what else can you do? Say, for example, can you make a story out of it? Or can you make a new picture out of the picture that you just see? So these are the higher level of digital processing. So the digital image processing at the very early stage of low-level image processing consists of, we know that we are beginning to look into this digital image. And in the past, whenever we need to send some images, we will have to send it through physical post, right? And so now, the very initial stage that people are trying to enable this computer to do is how do we send this picture from one place to another without sending them physically. And one of the methods is through digital image, where we are sending this pixel information from one location to another, and another person will be able to receive this and convert this into another image using these values. So these are the very low level of digital image processing. So then, in the medical field, there are also people are also beginning to use a lot of images for medical diagnosis. So then, what we are working on within these applications is how do we reconstruct these images and how do we sharpen or reduce the resolution in order to help with medical diagnosis. So those low-level image processing has been very helpful for a period of time, for a period of very, very long time in a lot of fields. So then as it evolves, the mid-level and high-level digital image processing, all of this that we have covered last week comes true. So we can see that people are beginning to look into representing humans using pictorial constructs. Then we also see that we have this algorithm which is able to identify human faces that is being used in digital cameras back then. And we have also seen that this mid-level digital image processing has enabled how this computer vision field flourish into what we see today, right? So that is about digital image processing. But the bottom line here is image classification is still the focus of this class, where we will be talking a lot about image classification, because that is the most important computer vision task in today's application. So in what kind of industrial applications do we need image classification? So whenever some human operators are expensive, whenever a business process is slow and unreliable, that is the time when computer vision recognition will come in. So we let the machine do the job, therefore the quality of work will not be impacted by how tired human eyes are, because computer can just work, right? So some of the example of computer vision applications are medical imaging, control system of circuit board of those circuit board manufacturers, some of the surveillance for law enforcement for of smart cities, things like that. So in the next section, what I'm going to share with you are some of the data sets which is available publicly, and they are not too big and not too small, and should be just nice for image classification task for your assignment. So one of the data sets which I found interesting is these blood cells images. So in the medical field, it is very blood cell classification is one of the very common tasks which is done by a pathologist. So what we are trying to do here is to have this labeled blood cells images labeled with its different blood cells. So what we are trying to do is to classify these images to identify whether the cells, no, the blood samples consist of what type of blood cells. So in case you are interested, this is an interesting one to work into. This has 4 classes of images, therefore it is a multi-class classification problem. Another one is a relatively simple one. It only has 2 classes, so it is a binary classification problem. So in this sample data set, we have 2 sets of images of different types of pistachios. So what we are trying to do is to train this computer system to differentiate between the different type of pistachio. As you can see from this image, the 2 types of pistachios can look very, very similar. So this is the time when a human classification of this pistachio can go wrong, and therefore we are trying to see if a computer would do a better task. And finally, I also have another one, which is rice data set. So for this rice data set, it is also again a multi-class prediction problem, multi-class classification. There are 5 types of rice images, where what we are trying to do is to train a model to differentiate these rice grains into 5 of these classes. Okay? So after sharing 3 of the data sets, let me know if any of the topic interests you at this point of time. Rice, blood cells, maybe others? Okay, let's look for others, and we'll share more in the next lecture. Okay, so for those who have found your interest in blood cells and rice, feel free to work on it. You can start looking into the images, you can start looking for literatures, and look for the applications. Yeah? So for those who are still not interested in any of these data sets, let's see if we can find something interesting, not too big, and just nice for this assignment next week. Yeah? So let's do it step by step. So now, as a summary, today we just covered real images versus digital image, areas of digital image processing, history, applications, and also components of digital image processing. So we are going to end this session right here. So before we end, if you have any question. So this is a very fundamental lecture about computer vision, and next week we are going a little bit more detail into how do we operate these images and what are the basis of image operations. What are we doing for practical later? For practical later, we are going to introduce you to Google Colab, the IDE that we will use. And then we will also look into how do some common packages that is used in computer vision. And we'll also show and try how to import image data into Google Colab, attendance code. There you go. What should you eat for dinner? What should you eat for dinner? Practical. Digital image. Can we stay here for the practical? Is the practical here or C706? So for this practical class, I will need I will need to have your computer to have sufficient power that would last for 1 hour. So do you have? Can your battery last for 1 hour? Huh? Then no, then we have to go to the lab. So the practical class will be at the lab. So let's go. Yes.
For the Cvnlp, I saw that this is the whole thing, right? But then when I saw your template for the work, so I need to follow which one?